Hello, everybody, and welcome to Everyday Leetcode. This is Tirth Doshi, and this is our problem today. And we are going to solve a very, very interesting problem. It's a tough problem, to be honest. It took me some 45 minutes to come up with a logic. And after coming up with the logic, the code was very easy, but it's a very, very interesting problem, I tell you. This will clear a lot of dynamic programming concepts. So if you do not know dynamic programming, then this video is definitely not for you, because dynamic programming is the basics of this problem. And yeah, so just like every time, let's just start with what the problem is, how do I approach the problem, and what the solution is. So that would be the structure of the channel. And this, let's understand what the problem is. So you are given a positive integer n. You need to find the least number of perfect squares which sum up to n. So for example, if you add a 12, so what are the perfect squares still there? 1, 4, and a 9. Can you add a 9 and a 9? No, you cannot add a 9 and a 9 to get a 12. Can you add a 9, 1, 1, 1? So yes, you can add this and get a 12. 9 plus 1 plus 1 plus 1 would be a 12. So 9 plus 3 is a 12. So the moment I saw this, 9 plus 3, it's a 12. I know there are 4. So I used 4 perfect squares to generate that. But in reality, I can take just 3 fours, 4 plus 4 plus 4, and tell you that I can make 12 with 3 perfect squares. 3 is the minimum answer. So that is why the answer is 3. That is why over your output is 3. Similarly, if you take 13, 13 is 9 plus 4, but it's also 9 plus 1 plus 1 plus 1 plus whatever, 9 plus 1, 9 plus 5, 9 plus 4, yeah. So 9 plus 4, and 4 can be written as 1 plus 1 plus 1 plus 1 also. So that would be either you have 2 or you have 9 plus 1 plus 1 plus 1. How much is that? 1 for 9 and 4 other ones. So that would be 5. So either 2 or a 5, which one is minimum? So it's 2, and that is why your output is 2. So this was understanding the problem. Okay. Now, one thing is observation. Always use your observation carefully and observe it slowly. We do not want to rush it. So let's observe things slowly. I saw that when I said 12 plus 9, what immediately came to my mind is that, okay, if I used 9 to get a 12, okay, I need to know what is the minimum amount that is required to get a 9. It's just a 1. So it's just one perfect square. Plus, what is the minimum amount that is required to get a 3 from perfect squares? So that is 1 plus 1 plus 1. So there are 3. So that is why I said that there would be 4 if I use 9 plus 3. Similarly, if the number would have been 4, okay, if I try to make the number 4 from if I try to utilize 4 to make the perfect square, so if I use 4 as a perfect square and some other other perfect square sum to add up to 12, so I take a 4, I need an 8. So I know that 4 requires only one perfect square to add to itself. So 4, that's 4. And if you take an 8, it requires 2 perfect squares. So 4 plus 4, that would be the minimum. And that is why your answer is 3. So that's the logic. So we are trying to just understand that we are always using this property a plus b is equal to my sum, then a has to be equal to sum minus b. So again we use this particular property. Okay, so one thing is that I saw that if I want to compute 12, the minimum number to get 12, I need to know the minimum number for 9, and I need to know the minimum number for 12 minus 9, which is 3. Or when I want to compute 12, I need to know the minimum number of 4, and I need to know the minimum number of 8. So that means my answer is dependent on previous answers. So whenever you see that my answer is dependent on previous answers, it means that it's a dynamic programming problem. Okay, if my answer was not dependent on the previous answers, there was no dynamic programming involved. That property itself is the optimal substructure. So if you know the optimal value for getting a sum of 9, and if you know the optimal value for getting a sum of 3, then you know the optimal value for 12. Similarly, if you know the optimal value for 4, if you know the optimal value for 8, then you know the optimal value for 12. Similarly, if you know 1 and 9, 9 and 3, again 3 and 9, again 1 and 1 and of 11. So if you know the optimal value of 11, if you know the optimal value for 1, then you can say that you can find out the optimal value. So it would be, so let's just assume as of now that I know the optimal value. Okay, so dp of 1 means that what is the minimum number, what is the least number of perfect squares required that sum up to 1. dp of 2 means what is the least number of perfect squares that sum up to 2. dp of 3 means what is the least number of perfect squares that sum up to 3. So I know that dp of 1 by simple logic has to be 1, because it's a perfect square. Anything, I will just require one perfect square that will sum up to, and that's the number itself. 2 is not a perfect square, so I find the minimum perfect square from 2, that's 1. So I can have 1 plus 1, so I will require 2 perfect squares that add up to 2. So the minimum is 1 here, 1 plus 1 plus 1. That's 1. The minimum is 1, as in the closest perfect square to 3 is a 1. So that is why you can have 1 plus 1 plus 1, and that is 3. So of course that is 3, but what I mean to say that there are 3 number of perfect squares. So that is why dp of 3 would be a 3. Okay, let's not confuse that. Similarly, dp of 4 would be equal to 1, because there is only one perfect square. I mean, the minimum number would be just 1. The minimum number over here would be a 4 plus 1. So you have 2 here. dp of 6, the minimum number 4 plus 2. So if I know the value of 4 plus 4, it's 1, and 2 is a 2, so it's a 3, and so on. So that's the assumption that I know it. Okay, now I have understood that there is optimal substructure, there is overlapping subproblems, that's a dp. I make a new array of dp. I try to compute things now. Now, when you see this optimal substructure overlapping subproblems, that's when you think about DP. So here is the approach. Okay, whenever you look at DP problems, all you need to see is the base case first, and then let's come up with another solution. Okay, so base case. So what should be the base case? When I saw the DP of 1, it was 1. DP of 2 was 2. DP of 3 was 3. DP of any perfect square would be always 1. So that's the base case. Okay. So DP of any perfect square of, let's say, 1, 2, or 3 as of now, not a perfect square. Let's forget that. Let's have the base condition as this. DP of I would be equal to I if I is less than equal to 3. So DP of 3 requires 3 numbers, DP of 2 requires 2 numbers, DP of 1 requires 1 number, and DP of 0 will require 0 numbers of perfect square. So that's how it is. So that is one base case. How about thinking some other base case? Always, if you take any perfect square, okay, DP of I would be equal to 1 such that I is a perfect square. So if for any perfect square, if it's 1, 4, 9, 36, every perfect square will always take just one perfect square, that's the number itself, to add up to that number. So that is why DP of I is this. Now the important condition comes. The important condition is that when I think about this important condition, I have to know what answers. So how do this answer 12 relate to my previous answers? So when I wrote DP of 12, I said it was the minimum of DP of 12 minus 9, so plus DP of 9, or it was DP of 12 minus 4 plus DP of 4, right? Or it was DP of 12 minus 1 plus DP of 11. So that's how it was. Yeah. And this minimum value gave me the answer. Okay, so this ideally is the approach. Now, if you see 9 is there, 4 is there, and a 1 is there, that means I have to store these perfect squares somewhere. So what I do first is, in this, now I'll tell you how I solved this problem. This was the logic behind the problem. Now solution is what makes things interesting. So I saw 12. What is the closest? So if I find the square root of 12, it might be 3 point something something something. Of course, square root in C++ might be a function. I did not use that. I'm not sure about that, so I didn't really use square root function. I got the square root of the number 12, and that was 3 in integer value. The moment I found a 3, I stored 1, 2, and 3. The squares of 1, 2, 3 in some subarray. So that was squares. I just made the square 1, 4, and a 9. This is another array that I used. After doing this, I had the squares. Now I needed to construct the DP table. So the DP table was constructed like this. First I handled the base case. So DP of I was equal to I for I ranging from 1 to 3. So for that's how I made it. And for if for integer I is equal to 4 to 12, what I did was this. If your 4 is present, if your I is present in squares array, I did a binary search. If it was present, it would return a true. Because the squares array is sorted, I can do a binary search. It would return me a true. If that returned me a true value, then I simply had to make dp of I is equal to 1. It's equal to 1, my bad. Because it's a perfect square itself. Next, I wanted to know that if, let's say that it's not present, dp of I would be equal to minimum of dp of I. So if now let me come to, so let's say if I wanted to find for 5, okay, what I used to do is I used to get the index that was closest to 5. So when I see that, and that was 4, and that index was 1 in my squares array. So what I did is I created a function get index that used to get me the index of the closest perfect square from that element. So if I was a 5 over here, my get index function, get index of 5 returned me a value 1. Okay, this returned me a value 1. So yeah, so this returned me a value 1. Why? Because 1 is the index where 4 is located. So I kept that value as like k. I called it k. Then from for I is equal to 0 to k, of course the squares of array I'm talking about, dp, because I am within I can call it j. From 0 to k, dp of this I would be equal to the minimum of my previous answer, dp of I, or it was dp of I minus squares of k. So it would be 5 minus 1 plus dp of 5 minus 1 was a 4. 5 minus 1 is 4, 4 and 4 is dp of squares of k. So that's how I solved it. Yeah, so this is how I solve this particular dp problem. Now let's take a look at the code. I know this is taking a little longer than normal, but it's very, very important to understand. Very important for us. DP is, it's a wonderful topic. People are really scared of it, but it's fun to solve it and come up with a solution. It feels really good. So if the number happens to be lesser than 3, I just return an n. If k is my square root of n, so k would be equal to, for 12, the answer k would have been 3. The square root is found using binary search technique, and this takes login time. Now I made a vector called as squares. Now from I is equal to 1 to 3, I will go and I will push the squares. So 1 into 1 is a 1, 4 and a 9 in the squares array. Now I initialize the dp of I into int max because I just wanted to, do the min. And for the first time, I always want that element to be really, really high. Okay, so that's just the initialization part. Then I said from I equal to 1 to 3, that's the base case that I wanted to handle, and that's what I explained below. 1 to 3, the dp of I would always be equal to I. For dp of 1 it's 1, dp of 2 is 2, dp of 3 is 3. That's what I just explained. Now from I equal to 4 to n plus 1 or I plus plus, if the binary search, there's a function called as binary search where you just put the starting and the ending, and you put the element to be searched here as the third parameter. It returns a true if the element is there, otherwise it returns a false. So if that element is there in the squares array, then it's just 1, that particular dp of I. Else what I do is, there is j, which is get index I comma squares. I pass the, but it's important to understand, I need to pass, so I is 5, let's consider I as 5, squares is the array that I'm trying to send, and I will send that array if 5 get index will return the index of the perfect square that is closest to 5. So get index function will return me 1. It will return me the index of 4 because the perfect square closest to 5 is 4. So how do I really do that? I just get the square root of 5. It's some 2 point something. So it's a 2. I just square that, which is 4. And I find in my squares array, where is 4? Which index? It's a binary search. I get that index. And that's my j. Now k will start from 0 up till that index. And it will just do what I said. It would take this, and yeah. Do you want to walk through an example? I think we have done enough. It's now just implementing this. If I walk through an example, how about walking through and making a TP array? Let's just walk through a smaller example at least. Let's say 6. Okay. So what's the square root of 6? It's 2 point something. 3 point. Yeah, it's 2. So 1 and 4 would be there in my DP array. Now DP of is 1. Let me make the DP array. DP of 1 would be a 1. DP of 2, this is the base case that I just handled. These are the indices. Yeah. Now for 4, it would be 1 because it's a perfect square. Then when for 5, it would be minimum of DP of 5 minus 4 plus DP of 4. So minimum of DP of 1, or it would be DP of 5 minus 1 plus DP of 1. So for 5, this is the value. DP of 5 minus 4, DP of 1 is a 1. So 1 plus DP of 4, DP of 4 is also 1. So it's a 2. So that is why you have a 2, because, and this is the index for index 5. Now for index 6 would be DP of 6 minus 4 plus DP of 4, or DP of 6 minus 1 plus DP of 1. So 6 minus 1 is nothing but it's a 5. So 5 will take 2 and DP of 1 is 1, so it's a 3. Or 6 minus 4 is taking a 2 plus 1, again 3 and 3, it's just 3. The answer is 3. The minimum of 3 comma 3 would be a 3. And yeah, so that's how we solve this problem. Please to practice this problem. Of course, you have understood this problem. It's a longer problem than normal, but please practice this problem. And I'm sure it will be very, very helpful. So that's all for today. Thank you.